This is going to be working with inflatables, and instead of compression or tension, we're going to be working with pressure. So if we look to nature again, right, the simplest case here of a pressure or pneumatic system is going to be a kind of soap bubble, right? Again, this is some research done by the Institute for Lightweight Structures, right, where they were documenting and diagramming the behavior of soap bubbles, right? And the key thing here is that if we have a kind of pneumatic structure, whereas before in the tension system we had only internal forces and anchor points that took up those internal forces, or the compression system where we had external force anchors and the forces internal to the system were resisting that external force. In this case, we have pressure, which is the internal force, so that inside the volume we have pressure that is being placed upon the surface at a perpendicular direction, right? So as we push out on the skin of the membrane or the pneumatic volume, right, the pressure is being taken up by that surface and distributed laterally across it, right? In this case, we're also anchored to the ground, so there's a little bit of a translation of some of the force down into the anchor point. But the key thing here is that we have a kind of perpendicular force that's acting everywhere on the surface. And again, we have both meridians and rings that we could describe within a kind of pneumatic structure like this, right? Some great examples of pneumatics in architecture and design. If we look back a little bit in time to Ant Farm and the Inflata cookbook, right, they have some really awesome sketches and kind of designs for inflatable structures and the kind of events and parties and stuff that would happen inside, right, based on pressure, high pressure, low pressure, and the volumes that would be designed for applying the pressure to. This one's called the Monkey Pod, right? And they also did a series of kind of installations. This is the Clean Air Pod, again from Ant Farm, where we have pressure being applied internal to a large volume, thereby creating a kind of inflatable system. And it is capable of taking on external loading from wind or gravity. They're usually very light, so the gravity is minimal if nothing at all. Or if you look at a more contemporary example like the Alliance Arena by Herzogenaurach de Meuron, this is more of a surface strategy, but each one of these is actually an inflatable element that then compose the entire skin, right? So it's both a solar and a kind of a surface treatment. All right, so let's go ahead and start to work with inflatables. So I'll save this file, and we'll be giving you, I'll give you both versions of this after the conclusion of the course in the instructor files. So let's take a look at what is involved in the inflatables section. All right, so a lot of this is going to look similar except for this part right here, all right, where we have to decide how the pressure is going to be applied. Everything else should be pretty much the same, all right? We were using the same kind of visualization technique as before, and the physics engine here. Okay, so let's go ahead, for the sake of time, let's start from what we've already done in this file so we don't have to set everything up once again. So I'm going to say this is my working file, and follow along with me. We should be able to take all of this section of the file and delete it. We'll go back through that part, right? But we're pretty familiar with compiling all of our force objects or physical objects, all of our anchor objects, and setting up our simulation controls. So I don't want to do that again. So we'll keep that part in the file, and then I'll actually go ahead and delete everything afterwards too, so we can go back through another way to visualize the pneumatics, the simulated pneumatic surface that's the result of the simulation. Okay, so let's go ahead and get this started. Let's see about using this actual exact same input that we had. So I'll take these 5 meshes and bring them in as our our input here so that we have a quad divide, right? And I'm going to add in some anchor points also. So I'll grab these ones around the outer edge and bring them into the input anchors, set multiple points. Okay, so now we're ready to build out the kind of part that's different relative to inflatables. Turn the preview on. We can see our mesh edges. Okay, so the pressure force, which is under a kangaroo, forces pressure, right? This force requires us to specify each point of a triangle for the pressure to be applied to. So remember, if we're looking back at this diagram here, this one, right? If this surface is composed of triangles, we can supply a pressure force that is perpendicular to each triangle face so that the direction of the pressure is consistent across all of them, right? And the accumulation of all those pressure forces is what's going to give us the resulting shape. Okay, so we need to somehow go from this mesh to organizing each one of the faces in on the mesh into a triangle. All right, so what we're going to do is we're going to take this mesh, which is divided, and look for a way to turn each one of these quads into triangles. So if we go to the Mesh tab, and under Utility, there's an option near the bottom that allows us to triangulate all quads in a mesh. That sounds good, right? We need to go to triangles. So let's use that object. I'm going to connect my mesh, quad divide mesh into the triangulate. So now I can see that I have triangulated every one of those quads, right? Based on how those initial quads were made, we're going to get triangulated in different directions, right? So you can see it kind of shifts right here in terms of the direction of the triangulation. That's okay. For our purposes, it's going to work out pretty well. All right, so as a result, we have the mesh only with triangle faces. All right, so what we're going to do is we need to go now from one mesh with, in my case, 1,000 faces to groups of 3 points. Right? Now, we know that the mesh elements, the things that make up a mesh, are faces, and each face is describing the connection between 3 or 4 vertices. Right? So we need to go from meshes, or one mesh, down to faces, and then for each face, grab each of the vertices that are part of that face to then apply our pressure to. Okay, so let's go ahead and do that, right? We're going to take our mesh and we're going to decompose it, just like we did before. So under mesh analysis, decompose, take our mesh, decompose it into vertices, which is one long list, the mesh faces, and these are our commands to say which 3 points should be connected, the colors and the normals. And we don't need to work with the last 2 outputs, but we do need to work with the vertices and the faces. Okay, so how do we go from the face command to individual values that describe which point or which vertex in the collection we're going to use? Well, we need to then take apart the faces themselves, right? So if we go to the Mesh Analysis tab, there's also face vertices. This will take in our face command and supply us with the numbers that describe the first, second, and third vertex in each one of the faces, right? And these are index values that correspond with this list of vertices. Okay, so how do we gather specific items from a list? Well, we're going to use our friend, the list item from sets list. Here's list item. All right, we're going to take the vertices as the list. The item to select is going to come from A, and we're going to do this 3 times. So I'll copy and paste this 2 more times. Use B and C. So now we have all of the first points in a face, second points, and third points. Right? So these are our vertices per face. Okay, so now we have point A, point B, point C, and then we can go directly into our pressure input for point 1, 2, and 3. All right, the last thing we need is a value to describe the pressure level. So I'm going to use a slider that's between 2 and 5 was the current default value, and 25, and hook that up. All right, so now as a result, our pressure out, we have a physical property, the kangaroo K pressure, right? This is going to allow us to calculate the pressure applied to each one of these mesh faces. Okay, so let's go ahead and plug that into the force objects. I'm going to use D2. All right, now if we go ahead and apply pressure to this mesh, even if we have it anchored, let's take a survey. Do you think that with the way we have it set up right now, which is pressure applied to each face and anchor points here at the corners, will this simulate as we expect, where these are anchored, this will kind of inflate, blow up a little bit, and bounce around and try and find an equilibrium shape? If you have a suggestion, go ahead and drop it into the questions window. All right, we have 20 yeses and 20 nos. All right, so we're split right down the middle. The answer is that it shouldn't work as we expected, but let's go ahead and see if we can examine what's actually going to happen, right? So I'm going to turn the physics engine preview on so we can see the particles, and go ahead and release my simulation, release my timer block, and all of our particles blew away. They went away very quickly, right? Now, the reason is that we have half of the inputs necessary for our pressure-based simulation, right? Because we have this force, which is the pressure. We have the anchor, but we don't have any ability to resist those forces, right, through the surface of the membrane or the inflatable. So what we have to do is go back and make sure that we're also constraining this equilibrium shape in addition to applying force to it. In order to do that, we're going to use the same utility that we did before, which was to get the springs from mesh, right? So this will constrain the surface. We take in our mesh, and we make another slider as we did before for our rest length factor. So I'll say maybe 0.75, less than 1, less than 2. There's our rest length. So now those are our springs, right? So that if we try again, and by adding that as a force object, right, the springs here will resist the pressure force, thereby creating an inflatable, right, or something that will behave very similar to an inflatable. All right, so a couple of quick things. This is an interesting one. I kind of like it. Let's visualize the mesh first, and then let's talk about the different ways that we can anchor the edge of our inflatable. All right, so I'm going to turn the timer block on, reset my simulation, and we're going to do the exact same thing that we did before, which is to recreate the mesh with the vertices that pass through the geometry input of our physics engine. All right, so we need to take the vertices of our mesh into geometry. We'll give this a wire display of faint to keep it clean. And then we're going to reconstruct the mesh afterwards. Geometry out. Face commands come all the way from back here. Again, we're going to turn the wire display to faint. All right, so that's face command to face command. Save this. Oops.